Good morning, grade 10. How are you today? Okay, so today we will continue our lesson, section 1, refraction. Before we continue it, I will show you this simulation about the refraction. Here we have air, and here we have glass. Okay, so here you can change it. I choose, for example, here the water. Okay, I can choose a glass. I choose it first, water. Okay, so this is the ray. So as you can see, this is the incident ray. Okay, this is the one here which is like light. It's the reflected ray, because when the light hits the surface, for sure part of it is reflected and part of it is refracted, enters the water. Because we said, girls, the light when it enters the water it slows down. Okay, so from a medium in which the light is faster to a medium in which the light is slower, the light bends how toward the normal. Okay, so see, the light doesn't go straight like as the original path. Instead it bends toward the normal. Okay, so here if I, for example, make the other uh, medium glass, so the refraction will be what more. See why? Because the light in glass is slower than the light in water. The glass, the particles are closer to each other. The particles are closer, therefore it's a more dense material, therefore for sure the light will slow down more. Okay, so this is the refraction. We talked about it in the previous time. And we talked also, girls, about the wavefront model. We said we can use the wavefront model, but usually in our drawing we will use what, the ray approximation, the ray like this one with arrows. So the arrow is very important to show the direction in which the light is going. See here, I can choose the other model, which is wavefront. Okay, so as you can see, wavefronts, they come here. Here you can see that the distance between these two the wavefronts, it diminishes. It's shortened, which is the wavelength, right? So the distance between two wavefronts, it is the wavelength. So the wavelength decreases here because the speed decreases, but the frequency, it doesn't decrease. The frequency, it's the same number of waves produced by second. Okay, per second. So the lesson is very easy. We will continue now. Today we will talk about law of reflection. So we have something called index of refraction. This index of refraction, like, it shows us, girls, how much will the light bend. Okay, so index of refraction for a substance is the ratio. It has a specific equation. It's the ratio of the speed of light in vacuum, which will be represented by the letter C. You know what is the speed of light in vacuum? It is 3 times 10 to the power of 8 meters per second, divided by the speed of light in the substance that we are talking about. Okay, so N, it represents the index of refraction. Okay, so it's equal to C, speed of light in vacuum, divided by speed of light in a medium. Okay, so N is the index of refraction, like it shows us how much will the light refract in a substance, the amount by which the light will refract. Okay, so N, we can say, girls, it is the measure of the optical density of a material. Like, in other words, the more dense the material is, the more N we have. Why? Because in a more dense material, such as glass, we know that the glass is more dense than water. Okay, type when the light enters glass, it will refract, it will bend, it will slow down more than in water. Okay, so when the density here like is more, okay, so N, measure of optical density. Okay, so N is more. N, it's an index of refraction, so it shows us that we will have more refraction in this material, which is the glass. Okay, so N always greater than 1, because light always travels slower in that substance, than in vacuum. The lowest value of N is N equal to 1. in vacuum and in air. Okay, so girls, see here, imagine that I'm talking about air, N for air. Okay, so every material, so girls, you will see that every material, every substance, it has a specific index of refraction. So air, it has a specific number, water, it has a specific number, glass, it has a specific number, diamond, it has a specific number. Okay, for example, I'm talking about air, so it is C divided by the speed of light in air. So I write my material as subscript here. Okay, what is C? It's 3 times 10 to the power of 8, right? 3 times 10 to the power of 8. And here, what is the speed of light in air? Okay, we know that the light slows down a little in air, but we said we take it approximately the same. So it's also 3 times 10 to the power of 8. So same number up and down, numerator and denominator. So the index of refraction in air or in vacuum, it is what? It is 1, which is the lowest index of refraction possible. Because if I talk about like N water, pay attention with me, N water, it is what? It's the speed of light in vacuum divided by the speed of light in water. The speed of light in water, girls, it's less than the speed of light in vacuum. So it is an amount less than 3 times 10 to the power of 8. Okay, it is 2 point something. So it's less than this. So the less this number is, what? The more this is. See, this one is constant. This one is constant. It's always what? 3 times 10 to the power of 8. Type here, denominator. So the less the denominator is, the more the index of refraction, and this is logic. So in water, because the speed of light in water is less than in air, so this amount we will have it what? More than 1. More than 1. So you are dividing 3 times 10 to the power of 8 divided by 2 point something times 10 to the power of 8. Okay, so for sure you will get it what? More than 1. Okay, so the bigger this number is, sorry, the smaller this number is, the bigger this number is. Okay, and for glass, what do you expect? For sure, for glass, the speed of light in glass is less. The light travels slowly in glass, slower than in water, slower than in air. So the index of refraction in glass is more. So these two, you see, they are inversely proportional. Okay, so the larger the N, the slower the light travels in that substance, and more bend we have, more refraction. We said at the beginning, the N, its index of refraction, meaning that more N, more refraction, lower N, lower refraction. Okay, so the greater N, more refraction occurs when light passes from medium with smaller N to a medium with larger N. What do you expect? So we are going to a medium which is what? More dense. So the light will slow down or speed up? Will slow down. So how will it bend? It will bend toward the normal. Such as from air to glass or from air to water. Okay? When light passes from a medium with large index of refraction to the one which has small index of refraction, small n, so from great N to small n, so we are entering a medium which is less dense than the first. Okay, so the light will speed up. So how will it bend? It will bend away from the normal. Here we have some examples. You have it in the book. Like cubic zirconia, here it has N equals to 2.2. Okay, diamonds 2.4. Okay, so here in these two substances, look, the light bends so much. Why? Because they are very dense materials. Okay, so that's why refraction inside them will be the highest. See, highest value of N, it means highest refraction. Okay, here refraction will be less. Okay, see, in air, it's approximately 1. We take it as 1, the index of refraction. No bend of light in air, because we are taking it like the speed of light in air, it is the same as the speed of light in vacuum. So N1, nothing, no refraction occurs. Okay, but when the light passes from air to water, here the refraction occurs. See, the index of refraction of water starts to be more than the one in air. Then in materials that are more dense, the index of refraction is more. Okay, so light slows down when it enters an optically denser medium. The refracted ray bends toward the normal. So imagine you are going from a material which is less dense to a material which is more dense. So light will slow down, it will bend toward. It doesn't go straight, it just bends toward the normal. And here we have an example, like if you have a car on a bench, you are moving it on a bench, okay, then it enters a place where we have paper with fine sand. So the car will not continue straight, it will rotate like this, it will bend toward the normal because it enters a material which is more dense here. Okay, so it slows down, it goes like this. But if we have the opposite, like when we are going from a material which is more dense to a material which is less dense, see, light speeds up when it enters an optically less dense material. The refracted ray, how does it bend now? See, this is the original path. How does it bend? It bends away. Okay, so I hope that it's clear. The second part for today, it's about why we see sometimes in objects in different positions. Okay, like here you have a pencil which appears to be bent, or you have, if you put spoon, it also appears to be bent. So why we see this one? Pay attention, I will explain it on this example. You have this example in your book. Let's say that I have a fish underwater and a cat outside. The cat is looking at the fish. First, the cat is looking at the fish. So cat is looking at the fish, so how is the light traveling? If I am looking at you, so the light should travel from you to my eyes in order like to see you. Okay, so here for the cat to be able to see the fish, the light is traveling from fish to the eyes of cat. So light, how is it traveling? From water to air. Type from water here. When it enters air, will it continue in the same path as it was in water? No, because it enters a material which is less dense. Light here is faster or slower? Faster. So how will it bend? Away from the normal. So the cat, girls, it receives this ray. And already we said in the first, or like the second section in the previous chapter, that whenever a ray enters my eyes, the brain directly understands that this ray has traveled how? In a straight path. Has traveled in a straight path. So the brain understands that, believes that the source that emits this ray, it's from here, not from here. And therefore the brain thinks that the object which is giving the light is here. Okay, so I will repeat it. Pay attention. The cat is looking at the fish. The rays coming from the fish, they are traveling through water, then they will go through air. Okay, when they enter a material which is less dense, here air, light is faster in air, so the ray will bend away from the normal. The cat will receive this ray. The brain understands that the ray has traveled, appears to be coming from a source on a straight path. Okay, so we understand that the source that's giving the light is here. Okay, second situation here, let's say that the fish is looking at the cat. Okay, so the rays should come, all of them, from the cat to the fish, for the fish to be able to see the cat. So the rays, how are they traveling now? From air to water, from a material in which light travels faster to a material in which light travels slower. How will it bend? It will not stay the same thing. It will bend. How? Toward or away? For sure toward, because it slows down. So the fish catches or receives this ray, and the brain assumes or understands that this ray has traveled how? In a straight path. So the fish believes, understand that the source that emits this ray, that gives to it this ray, is this one, not this. And therefore it sees the cat where? Above its original place or its correct place. So here we can understand from situation number 1 that whenever we look at something underwater, we see it closer than it really is. Okay? And we can understand from situation number 2 that whenever we look, if we are underwater, or animals or anything underwater, looking at something above water, we receive it farther than it really is. Okay? So this is the explanation. I already said it. So here for sure this and this, they are just virtual images of the real fish. This is the real fish. This is an image of the fish, so we call it a virtual image. This is the real cat. This is an image of the cat. We call it virtual image of the cat. Okay. So this is everything for today.